it's on now. So you want to watch video?
Yeah, sure.
I'll share. I'll share the screen.
Let's say I have some function f that is continuous on an interval between a and b, and I have these brackets here, so it also includes a and b in the interval. So let me graph this just so we get a sense of what I'm talking about. So that's my vertical axis. Horizontal axis. I'm going to label my horizontal axis t so that we can save this for later. I can still make this y right over there, and let me graph this right over here is the graph of y is equal to f of t. Now, our lower endpoint is a, so that's a right over there. Our upper boundary is b. Make that clear. Actually, just to show that we're including that endpoint, let me make them bold lines, filled in lines. So lower boundary a, upper boundary b. We're just saying, and I've drawn it this way, that f is continuous on that. Now, let's define some new function. That's the area under the curve between a and some point that's in our interval. Let me pick this right over here, x. So let's define some new function to capture the area under the curve between a and x. Well, how do we denote the area under the curve between two endpoints? Well, we just use our definite integral. It's our Riemann integral. It's really that right now, before we come up with the conclusion of this, it really is the area under the curve between two endpoints. So this right over here, we can say is the definite integral from a to b, from a to x, I should say, from a to x of f of t dt. This right over here is going to be a function of x, and let me make it clear where x is in the interval between a and b. This thing right over here is going to be another function of x. This value is going to depend on what x we actually choose. So let's find this as a function of x. So I'm going to say that this is equal to uppercase f. So all fair and good. Uppercase f of x is a function. You give me an x value that's in between a and b. It'll tell you the area under lowercase f of t between a and x. Now the cool part, the fundamental theorem of calculus. The fundamental theorem of calculus tells us, let me write this down because this is a big deal. Fundamental theorem, that's not an abbreviation. Theorem of calculus tells us that if we were to take the derivative of our capital F, so the derivative, let me make sure I have enough space here. So if I were to take the derivative of capital F with respect to x, which is the same thing as taking the derivative of this with respect to x, which is equal to the derivative of all of this business. Let me copy this. So copy and then paste, which is the same thing. I've defined capital F as this stuff, so if I'm taking the derivative of the left-hand side, that's the same thing as taking the derivative of the right-hand side. The fundamental theorem of calculus tells us that this is going to be equal to, f, lowercase f of x. Now, why is this a big deal? Why does it get such an important title as the fundamental theorem of calculus? Well, it tells us that for any continuous function f, if I define a function that is the area under the curve between a and x right over here, that the derivative of that function is going to be f. So let me make it clear. Every continuous function, every continuous f has an antiderivative, has an antiderivative, derivative, capital f of x. That by itself is a cool thing. But the other really cool thing, or I guess these are somewhat related, is remember, coming into this, all we did, we just viewed the definite integral as symbolizing as the area under the curve between 2 points. That's where that Riemann definition of integration comes from. But now we see a connection between that and derivatives. When you're taking the definite integral, one way of thinking, especially if you're taking a definite integral between a lower boundary and an x, one way to think about it is you're essentially taking an antiderivative. So we now see a connection. And this is why it is the fundamental theorem of calculus. It connects differential calculus and integral calculus. Connection between derivatives and, or maybe I should say antiderivatives, derivatives and integration, which before this video we just viewed integration as area under curve. Now that we see it has a connection to derivatives. Well, how would you actually use the fundamental theorem of calculus? So maybe in the context of a calculus class. And we'll do the intuition for why this happens or why this is true and maybe a proof in later videos. But how would you actually apply this right over here? Well, let's say that someone told you that they want to find the derivative. Let me just in a new color just to show this as an example. Let's say someone wanted to find the derivative with respect to x of the integral from, I don't know, I'll pick some random number here. So pi to x of, I'll put something crazy here, cosine squared of t over the natural log of t minus the square root of t dt. So they want you to take the derivative with respect to x of this crazy thing. Remember, this thing, this thing in the parentheses is a function of x. Its value, it's going to have a value that is dependent on x. You give it a different x, it's going to have a different value. So what's the derivative of this with respect to x? Well, the fundamental theorem of calculus, it tells us it can be very simple. We essentially, and you can even pattern match up here, and we'll get more intuition of why this is true in future videos, but essentially everywhere where you see this right over here is an f of t, everywhere you see a t, replace it with an x, and it becomes an f of x. So this is going to be equal to cosine squared of x over the natural log of x minus the square root of x. You take the derivative of the indefinite integral where the upper boundary is x right over here, it just becomes whatever you were taking the integral of, that as a function, instead of t, that is now a function of x. So it can really simplify sometimes taking a derivative, and sometimes you'll see on exams these trick problems where you have this really hairy thing that you need to take a definite integral of and then take the derivative. And you just have to remember the fundamental theorem of calculus, the thing that ties it all together, connects derivatives and integration, that simplify it by realizing that this is just going to be, instead of a function of f of lowercase f of t, it's going to be lowercase f of x. Let me make it clear. In this example right over here, this right over here was lowercase f of t, and now it became lowercase f of x. This right over here was our a. And notice, it doesn't matter what the lower boundary of a actually is. You don't have anything on the right-hand side that is in some way dependent on a. Anyway, hope you enjoyed that. In the next few videos, we'll think about the intuition and do more examples making use of the fundamental theorem of calculus. Let's say that we have capital F of x as being equal to the definite integral from pi to x of cotangent squared of t dt. And what we're curious about finding is the derivative of this business. We want to figure out what f prime of x is equal to. Well, this is a direct application of the fundamental theorem of calculus. This is just going to be the derivative with respect to x of all of this craziness. So let me just copy and paste that. So copy and paste. So it's just going to be the derivative with respect to that. And the fundamental theorem of calculus tells us that this is going to be equal to just this function, but it's not going to be a function of t anymore. It's going to be a function of x. So it's going to be equal to cotangent squared of x. And you'll often see problems like this if you go to calculus competitions or things like that, and or maybe certain exams. It's like, oh my God, I have to take the antiderivative of all of this business, evaluate it at the different boundaries, and then I got to take the derivative. No, you just apply the fundamental theorem of calculus. It's actually a very straightforward and a very fast thing to do. Now, let's mix it up a little bit. Let's say that you had the expression, the definite integral from pi, instead of from pi to x, let's say it's from pi to x squared. Let me write that x squared in a different color just to make it clear what I'm doing. From pi to x squared of cotangent squared of t dt. And you wanted to take the derivative of this business. So you want to take the derivative with respect to x. You want to take the derivative with respect to x of this business. How would you do it? Well, the recognition here is that this is capital F of x was defined as this. Now instead of an x, you have an x squared. So this is the exact same thing as taking the derivative with respect to x of capital F of not x, that would be this. Instead, we have capital F of x squared. Where we had an x here before, we now have an x squared. We now have an x squared. You can verify. If you had capital F of x squared, every place where you saw the x here would be an x squared. So it would look exactly like this. And so we just have to apply the chain rule. So this is going to be equal to, and this is going to be equal to the derivative of f with respect to x squared. So it's going to be, this is just straight out of the chain rule, it's going to be f prime of x squared times the derivative with respect to x of x squared. This is the derivative of f with respect to x squared, and then times the derivative of x squared with respect to x. This is just the chain rule right over here. So what's f prime of x squared, the derivative of f with respect to x squared? Well, if you evaluated f prime at x squared, instead of just being cotangent squared of x, it's going to be cotangent squared of x squared. So this part right over here, this business right over here is going to be cotangent squared of x squared So this is the derivative of all of this business with respect to x squared, and then you have to multiply that. You have to multiply that times the derivative of x squared with respect to x, which is just 2x. So there you have it. The derivative of this, all this craziness, is equal to 2x cotangent squared of x squared. Let's say that we've got some function f that is continuous on the interval a to b. So let's try to see if we can visualize that. So this is my y-axis. That's my y-axis. This right over here. I'm going to make it my t-axis. We'll use x a little bit later, so I'll call this my t-axis. And then let's say that this right over here is the graph of y is equal to f of t. Y is equal to f of t, and we're saying it's continuous on the interval from a to b. So this is t is equal to a, this is t is equal to b, so we're saying that it is continuous. It is continuous over this whole interval. Now, for fun, let's define a function capital F of x, and I will do it in blue. Let's define capital F of x as equal to the definite integral from a as a lower bound, to x of f of t, let me do that, of f of t dt, where x is in this interval, where a is less than or equal to x is less than or equal to b, or that's just another way of saying that x is in this interval right over here. Now, when you see this, you might say, oh, you know, the definite integral, this has to do with differentiation and antiderivatives and all that. But we don't know that yet. All we know right now is that this is the area under the curve f between a and x. So between A and let's say this right over here is x. So f of x is just this area right over here. That's all we know about it. We don't know it has anything to do with antiderivatives just yet. That's what we're going to try to prove in this video. So just for fun, let's take the derivative of f, and we're going to do it just using the definition of derivatives and see what we get when we take the derivative using the definition of derivatives. So we would get, so the derivative f prime of x, well, this definition of derivatives, it's the limit as delta x approaches 0 of capital F of x plus delta x minus f of x, all of that over delta x. This is just the definition of the derivative. Now, what is this equal to? Well, let me rewrite it using these integrals right up here. This is going to be equal to the limit as delta x approaches 0 of, what's f of x plus delta x? Well, put x in right over here. You're going to get the definite integral from a to x plus delta x of f of t dt. And then from that, you are going to subtract this business, f of x, which we've already written as the integral from a, the definite integral from a to x of f of t dt, and then all of that is over delta x. All of this is over delta x. Now, what does this represent? Remember, we don't know anything about definite integrals as somehow dealing with something with an antiderivative and all that. We just know this is another way of saying the area under the curve f between a and x plus delta x. So it's the area under the curve f between a and x plus delta x. X plus delta x. So it's this entire area. Right over here. So that's this part. We already know what this blue stuff is. This blue stuff, that same shade of blue. So this blue stuff right over here, this is equal to all of this business. We've already shaded this in. It's equal to all of this business right over here. So if you were to take all of this green area, which is from a to x plus delta x, and subtract out this blue area, which is exactly what we're doing in the numerator, what are you left with? Well, you're going to be left with, what color have I not used yet? Maybe I will use this pink color. Well, no, I already used that. I'll use this purple color. You're going to be left with this area. You're going to be left with this area right over here. So what's another way of writing that? Well, another way of writing this area right over here is the definite integral between x and x plus delta x of f of t dt. So we can rewrite this entire expression, the derivative of capital F of x, this is capital F prime of x, we can rewrite it now as being equal to the limit as delta x approaches 0. This I can write as 1 over delta x times the numerator, and we already figured out the numerator, the green area minus the blue area is just the purple area, which is, and another way of denoting that area is this expression right over here. So 1 over delta x times the definite integral from x to x plus delta x of f of t dt. Now this expression is interesting. This might look familiar from the mean value theorem of definite integrals. The mean value theorem of definite integrals tells us, so the mean value theorem of definite integrals tells us there exists a c in the interval. So I could c where, I'll write it this way, where a is less than or equal to c, which is less than, or actually let me make it clear, the interval that we now care about is between x and x plus delta x, where x is less than or equal to c, which is less than or equal to x plus delta x, such that the function evaluated at c, so let me draw this c. So there's a c someplace over here. So if I were to take the function evaluated at this c, so that's f of c right over here. So if I were to take the function evaluated at the c, which would essentially be the height of this line, and I multiply it times the base, this interval, if I multiply it times the interval, and this interval is just delta x plus delta x minus x is just delta x. So if we just multiply the height times the base, that this is going to be equal to the area under the curve, which is the definite integral from x to x plus delta x, x to x plus delta x of f of t dt. This is what the mean value theorem of integrals tells us. If f is a continuous function, there exists a c in this interval between our two endpoints, where the function evaluated at the c is essentially, you can view it as the mean height. And if you take that mean value of the function and you multiply it times the base, you're going to get the area of the curve. Or another way of rewriting this, you could say that f of c, there exists a c in that interval where f of c is equal to 1 over delta x, I'm just dividing both sides by delta x, times the definite integral from x to x plus delta x of f of t dt. And this is often viewed as the mean value of the function over the interval. Why is that? Well, this part right over here gives you the area, and then you divide the area by the base and you get the mean height. Or another way you could say it is, if you were to take the height right over here, multiply it times the base, you get a rectangle that has the exact same area as the area under the curve. Well, this is useful because this is exactly what we got as the derivative of f prime of x. So there must exist a c such that f of c is equal to this stuff, or we could say that the limit, let me rewrite all of this down in a new color. So there exists a c in the interval x to x plus delta x where f prime of x, which we know is equal to this, we can now say is now equal to the limit as delta x approaches 0. And instead of writing this, we know that there's some c that's equal to all of this business of f of c. Now we're in the home stretch. We just have to figure out what the limit as delta x approaches 0 of f of c is. And the main realization is this part right over here. We know that c is always sandwiched in between x and x plus delta x. And intuitively, you could tell that, look, as delta x approaches 0, as delta x, as this green line right over here moves more and more to the left, as it approaches this blue line, the c has to be in between, and so the c is going to approach x. So we know intuitively that c approaches x as delta x approaches 0, or another way of saying it is that f of c is going to approach f of x as delta x approaches 0. And so intuitively, we could say that this is going to be equal to f of x. Now you might say, okay, that's intuitively, but we're kind of working on a little bit of a proof here, Sal. Let me know for sure that x is going to approach c. Don't just do this little thing where you drew this diagram and it makes sense that c is going to have to get closer and closer to x. And if you want that, you could just resort to the squeeze theorem. And to resort to the squeeze theorem, you just have to view c as a function of delta x, and it really is. Depending on your delta x, c is going to be further to the left or to the right, possibly. And so I can just rewrite this expression as x is less than or equal to c as a function of delta x, which is less than or equal to x plus delta x. So now you see that c is always sandwiched between x and x plus delta x. Well, what's the limit of x as delta x approaches 0? Well, x isn't dependent on delta x in any way, so this is just going to be equal to x. What's the limit of x plus delta x as delta x approaches 0? Well, as delta x approaches 0, this is just going to be equal to x. So if this approaches x as delta x approaches 0, and it's less than this function, and if this approaches x as delta x approaches 0, and it's always greater than this, then we know from the squeeze theorem or the sandwich theorem that the limit as delta x approaches 0 of c as a function of delta x is going to be equal to is going to be equal to x as well. It has to approach the same thing that and that is. It's sandwiched in between. And so that's a slight, we resort to the sandwich theorem. It's a little bit more rigorous to get to this exact result. As delta x approaches 0, c approaches x. If c is approaching x, then f of c is going to approach f of x. And then we essentially have our proof. F is a continuous function. We defined f in this way, capital F in this way, and we were able to use just the definition of the derivative to figure out that the derivative of capital F of x is equal to f of x. And once again, why is this a big deal? Well, it tells you that if you have any continuous function f, and that's what we assumed that f is continuous over the interval, there exists some function, there exists a function, you can just define the function this way, as the area under the curve between some endpoint or the beginning of the interval and some x. If you define a function in that way, the derivative of this function is going to be equal to your continuous function. Or another way of saying it is that you always have an antiderivative, that any continuous function has an antiderivative. And so it's a couple of cool things. Any continuous function has an antiderivative. It's going to be that capital F of x. And this is why it's called the fundamental theorem of calculus. It ties together these two ideas. And you have differential calculus, you have the idea of a derivative, and then in integral calculus, you have the idea of an integral. Before this proof, all we viewed an integral as is the area under the curve. It was just literally a notation to say the area under the curve. But now we've been able to make a connection, that there's a connection between the integral and the derivative, or a connection between the integral and the antiderivative in particular. So it connects all of calculus together in a very, very, very powerful, and we're so used to it now, and now we can say almost a somewhat obvious way, but it wasn't obvious. Remember, we always think of integrals as somehow doing an antiderivative, but it wasn't clear. If you just viewed an integral as only an area, you would have to go through this process, say, wow, no, it's connected. It's connected to the process of taking a derivative.
Do you want me to play again this one, or are you good?
I think I'm okay. I guess we'll see how this goes.
Okay. So I guess this is the last one we need to watch, right?
Yeah, if we have trouble with the worksheet anyway. Which we probably will, since I have no idea what's going on.
Do you want to watch it? Do you want me to play this one too then?
Yeah, sure.
Okay.
We'd like to talk about the proof of the first part of the fundamental theorem of calculus. If you recall, that theorem says that if I have a function, cap f of x, defined using this integral, if my integrand, little f of t, is continuous, then big F of x is continuous, and the derivative of big F of x is actually little f of x. So in order to talk about this theorem, we need to know what f of x is. So if we look at it on graphically, let's assume that f of t is positive, and let's say that here is a, and here is x. Now this is the definite integral, and if our function is above the x-axis, then this definite integral represents the area from a to x under the curve f of t and above the x-axis. So what does that represent geometrically? Well, it's the area below f of t and above the x-axis between a and x. All right, we are particularly interested in finding the derivative of big F, so we need to use the definition of the derivative and express f prime using the definition of the derivative. So stop the video and write the definition of the derivative of big F prime. Okay, the definition of the derivative says that I have the limit of f of x plus h minus cap f of x, all of that over h. So what is f of x plus h? Well, let's go back to our definition of what f of x is. I'll need to replace every x in that definition with x plus h, e to x plus h of f of t dt. Represent, well, graph f of t, that is a t. Here's a x plus h. So f of x plus h would represent the area from a to x plus h. Now, if I have the area from a to x plus h minus the area from a to x, what is this difference geometrically? Well, it's the area between x and x plus h, this little part. All right, well, we want to be able to work with our function f of x, so we need to replace this expression f of x plus h and f of x with our integral expression. So stop the video and write the definition of the derivative of f prime, big F prime, using the integral definition. Okay, f of x plus h is the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt, all of that over h. Now, in order to do what I need to do, I need for this to be a sum as opposed to a difference. And so what I'd like to do is reverse these integration limits and make that a plus sign. So we will have, using the properties of integrals. So as h goes to 0, we'll have the integral from a to x plus h of f of t. Why? If I want to do that, I have to reverse from x to a my integration limits. All of that over h. Now, because I've rearranged these and this is now a sum, I can switch the order because addition is commutative. So let's switch the order and we'll have f prime of x equal to the limit as h goes to 0 of the integral from x to a of f of t dt plus the integral from a to x plus h f of t dt, all of that over h. All I did was reverse the order there. Now, if I have an integral that goes from x to a, and then from a to x plus h, I could add these two integrals together and just go from x plus h. So we'll have the limit as x plus h, as h goes to 0, of the integral, hang on, the integral from x to x plus h of f of t dt over h. All right. Do you remember the mean value theorem? The mean value theorem we studied when we talked about the average value of a function. The mean value theorem guarantees that if my integrand, my f of little f here, if f of x is continuous on AB, then the integral from a to b, then there has to be some point, then there is a point C in that interval from a to b where f of c times h has to equal the integral from a from x to x plus h of f of t dt. In other words, there has to be a point C somewhere in this interval between x and x plus h where the height, if I made a rectangle based on the height at C, the area of the curve x and h. Right. So the interval right here is equal to f of c times h. So as h goes to 0, the limit as h goes to 0 of, well, let's go ahead. The interval from x to x plus h, f of t dt. In place of that, we're going to put f of c, as h goes to 0, f of c times h, because of the mean value theorem for integrals, over h. Those h's cancel, and we get f of c. Well, now let's just think for a minute. As h goes to 0, think about what happens to c. Here's c. As h goes to 0, this x plus h is going to go toward x. What's going to happen to c? Well, as h goes to 0, c is going to go to x. And f of c is going to go to f of x. And that's what we wanted to show, that the derivative f prime of big F prime of x is equal to little f of x. F prime of x
Did you write them all down?
No, actually I didn't because my Wi-Fi died in the middle of the video.
Oh, do you want me to go back?
So if you could just go back to a minute or so.
Okay.
x is equal to little f of x. X is equal to
Okay. Okay, I got it.
Okay. So I guess that's all for this one. Do you have a question or are you good?
No, I think I'm okay.
So I'll put this link on the email.
All right.
It was nice to see you, Sam.
You too. I hope you do good. See ya.
Have a good week.